Yeah. Is it true that every C infinity germ can be approximated by an analytic germ in the following way? F in C infinity, for every F in C infinity, there is a C omega germ G, such that the n derivative of F minus the n derivative of G is bounded for every n. So if there is a positive answer to that, then I think, well, I think I've verified that maximal C analytic Hardy fields are also eta 1. Anyway, just if anyone in the audience has any idea about this, I mean, there is a literature, there's certainly plenty of literature about approximating well-behaved functions by analytic functions. But here, of course, the approximation is in terms of is for germs, and in this sense of but perhaps someone knows literature that can shed light on this. Maybe it's known, or maybe it's known that it's wrong. That would be a pity, but okay. So I mean, it's certainly well known, for example, that a C infinity or even a continuous function, continuous germ, can be approximated by an analytic germ in the sense that the absolute value of the difference is let's say less than equal to 1 ultimately. That kind of thing is certainly well known. But here, of course, you have to look at the differences between the n derivatives for every n simultaneously, and that makes it tricky. Okay, so let me now. Last time I talked about pseudo convergence and reduced it for Hausdorff fields to something that's more manageable. So now I'm talking about pseudo convergence in Hardy fields. So convergence Hardy fields. And so H will be a Hardy field now. And we will fix germs, sequence of germs, rapidly decreasing, so to say, in size. Yeah, they are all positive, and that is so we have the PC sequence, the Cauchy sequence, F sub I. F sub I is sum of the first is partial sum, and we want to show that this has a pseudo limit. Yeah, want to show Fi pseudo converges to some F in a Hardy field extension for some F for some H Hardian F. In other words, germ in a Hardy field extension of H. Right. Now, right. Now there is no, in order to do this, I mean, this is what we are trying to do, and we can do this. To prove this, of course, you can always go to a bigger Hardy field, right? It remains a right. So can always increase. Go to a Hardy field extension to say an H-closed Hardy field extension. H-closed, you know, Liouville closed, omega-free, Newtonian. So it has, of course, that we can do that because of our main theorem. H closed Hardy field extension of H. Okay. No loss of generality in doing that, and now we can state the following key fact, key lemma. So suppose it's already H closed, yeah? Let H be H closed. So in particular, it contains all real numbers. And of course, in order to show that that this capital Fi's pseudo-converge, can assume that it does not have a pseudo limit in H itself, otherwise it would be done. Yeah, that H, and suppose I there's no pseudo-converge. H itself, and suppose we have some kind of sum construction, like the one that infinite sum construction, like the one I presented last time, but actually one has to modify that a bit, as we will see. Suppose we have a candidate pseudo limit. Yeah. So that's F. Yeah. So think of this as a sort of candidate and a reasonable infinite sum of these of the little Fi's that you might think is a pseudo limit. Then the following are equivalent. And one, Fi pseudo converges. Oh, well, of course, for that, we have to say that F actually, I have to be a bit more careful in stating that, because this is makes only sense when F is actually in an ordered field extension. So, so I should say F is Hardian over H. So it lies in a Hardy field extension, and therefore an ordered field extension, and so it makes sense then to say that Fi pseudo converges. Right, that's what we want. And now the following useful test for that, for all natural numbers k less than n, an active phi in H, phi in H bigger than 0. Yeah, remember this simply means that i.e. if you change the derivation by multiplying it by 1 over phi, it's small. It preserves the property of if you apply it to an infinitesimal term in H, then it's still for all such k less than m, an active phi, you have the following inequality. Delta k, the kth iterate of, well, we'll call this delta later on, of f minus fm, little fm, is bounded. Now you have to make sure that this makes sense, right? F is for the moment only in here. This is a germ also in this ambient differential ring. And so where delta is inverse the usual derivation as a derivation on this ring. As a derivation. Ambient ring, differential ring. Right, so these are the key inequalities that have to be established. Okay. And so I'll prove it. Well, I'll prove it modulo some facts from our book. And this is the one point where we really need to use our main theorem that every Hardy field can be extended to H closed one. Never. That is the only point where this is used. But it seems to be an essential use. I don't see how one can get around it. Okay, now, I mean, we are really only interested in the implication from 2 to 1 because we are going to verify 2 in order to get 1. And that is a non-trivial implication. From 1 to 2 is much easier, but I will still do it because it's give you a sense why this is a reasonable thing to want, to require. 1 implies 2. This is kind of trivial. The thing is, assume 1. So we know that then F is in a Hardy field extension, and then this will be well, the thing is that F minus Fm, what is see, since F is a pseudo limit of the F of the Fm's, this will be dominated by well, actually, yeah, think of this secretly as Fm plus 1 plus Fm plus 2, etc. And so this will be actually strictly dominated by Fm in this Hardy field extension. So F minus Fm is infinitesimal, and so since for active P 0 delta this is now a small derivation in this also on this bigger Hardy field, which capital F lies. When you apply any iterate of this derivation to this infinitesimal element, it will still be infinitesimal. And bigger than k. Well, in fact, for all mk and any mk, doesn't matter really. Any mk, delta K F over Fm. Since all this is now taking place in this Hardy field extension, capital F large, will also be infinitesimal. And so, so you see, this is really from 1 to 2, basically obvious. And you get actually more, not just for K less than M, all M and K. And, okay. But the interesting implication for us is 2 and part 1. Assume 1, assume 2. Now we are going to use it H is here. Since H closed, Fi does not pseudo-converge in its it is this species sequence is actually what we call differentially transcendental over H. Fi transcendental. This is a term that is defined in chapter 4 of our book. H. H defined, and well, I guess you'll need to chapter 4 and chapter 11. Chapter 4 gives the definition of deep transcendental. Well, wait a minute. It's not just chapter 4 and chapter. I think you really need various chapters in our book. I'm afraid that you need later chapters as well. But anyway, this means that this sequence, pseudo-Cauchy sequence, has no pseudo limit in any differentially algebraic immediate H field extent, not just Hardy field extent. Doesn't have any pseudo limit in any immediate D-algebraic H field extent. That's a very strong statement, and it has certain consequences. Yeah, so here you unfortunately you need a pretty good knowledge of some of the facts in our book that I cannot really summarize in briefly. Okay, so now let P be some polynomial, differential polynomial over H. Non-zero. So in order to show that capital F is Hardian over H, yeah, we'll need to show, we'll show, first of all, that F minus Fm well, we'll show F minus Fm is dominated by Fm and Pf that will, and Pf is a unit. It's actually ultimately non-zero as a germ in this ring. So you can invert it. And since if this Okay. Well, this is kind of almost obvious from the first thing. If you apply this for k is 0, you get gives you f minus fn. Fn. You apply it for k is 0, you get that this is bounded. So f minus fn is dominated by fm, but fm dominates. Wait a minute. Yes, fm dominates fm plus 1. So this is not exactly the same as strictly dominated, but in some sense it doesn't make any difference. Why is that? Okay.
Maybe like f minus fm minus fm. Correct. F minus big fm minus little fm. There's non-strictly dominated.
Say it again. F.
Big F minus big fm minus little fm.
Yeah. What about it?
This is the same as big F minus big fm plus 1, so it's non-strictly dominated.
Big F big is big F minus
Big fm plus 1. Because fm plus 1 is fm plus little fm.
F. Wait a minute. Fm plus 1. It's not. Wait a minute. This is you think of this as little fm plus 1 plus. Anyway, it's not. It's a routine thing to derive from this because this is true for all m. Easy to derive. It's not too important actually. After all, I could have replaced in this condition dominated by 1 by strictly dominated by 1. It makes no difference for what I'm actually proving. Easy to derive f minus f m. Yeah, strictly dominated by m. There's some trivial manipulation that nevertheless, when you have to do it on the blackboard, is hard to remember. So so this is not let's say done. It's basically just case k is 0 of this, and in fact it would also be okay. The thing is, we want to prove that if you plug in capital F for capital Y, you get some germ that is a unit, and that will be enough to show that it generates a Hardy field over H, right? Because it means that because it's true for every differential polynomial P not equal to 0, they can all be inverted. All these values can be inverted, and so you get the ring generated, differential ring generated by capital F over H is then an integral domain of which you can form the diffraction field inside here. Okay. Anyway, let's not get distracted by this minor point. Okay. Now, the main thing, the fact that this is transcendental over H, by various results in our book, had the following consequence. By chapter 11, H. that the Newton degree. So here we really are using this Newton degree of P, not but then a certain affine transform of it, namely Fm plus Fmy is 0. For all sufficiently large, let me see, for m big enough, for sufficiently large, there are what you really get is expressed more as a sort of in terms of additive and multiplicative conjugates of P, but you see this is an additive conjugate of P followed by a multiplicative conjugate of P, and since we are dealing here with a PC sequence of D transcendental type, if you and you do various manipulations to get this. So I'm just going to assume this. So take such an M which is bigger than the order. Which is greater than the order of P. Let's call it the R. The order of, and let's simplify notation and call this Q. That's Q. Q is now a differential, simply this affine transform. And let's figure out what this says. Transform of our original differential polynomial, and okay, so that means Newton degree of Q. This is 0. But what is this? This is simply the dominant degree of a certain compositional conjugate. The dominant degree of Q is compositional conjugate for active, for all sufficiently small active in H, P greater than 0 in H. Okay, and so take such phi, for such phi, you see the dominant degree of a differential polynomial being 0. What does that mean? It means that the degree 0 term, yeah, the term that does not involve any of the y prime, etc., strictly dominates all the other terms, all the evaluation of, strictly dominates the coefficient of all the other terms that do involve y or y prime. Such phi, 2 phi equals, so I'm writing here the term that does not involve any of the y's, and then the sum over all j of 0 h j y to the power j. I'll write the here h is a non-zero element. H. All hj are strictly dominated by and J ranges, J simply application for both of these tuple J0 Jr and power 1 plus R, and y to the j is application for y to the power j0, y prime to the power j1, y r to the power jr. And of course, this is only a sum of finitely many terms, a finite set of j's. And the coefficients h and hj are all in H itself. Or if you also say in H phi, compositional conjugate, they have the same underlying. But anyway, right. And I just wrote down what it says, the Newton degree is 0. And now we are going to plug in for y something that makes this equal to capital F. Right. So what is it that we have to plug in there for y? F. Yeah. So here we set G, capital G equals to F minus Fm divided by little fm. So G is bounded. So this is for the moment just an element of this ambient differential ring, but it will be bounded, and F is indeed now Fm plus Fmg. Right? We are, and so now we are going to plug in this last. Going to plug in capital G for y. Of course, all these computations are taking place in this ambient ring, C less than infinity. G, then P, then PF, same as Q of G. And of course, Q of G is the same as Q phi of G. But Q phi of G, we know, is H plus summing over all these tuples different from 0, Hj, G to J. Yeah, in C less than infinity. Right, now you have to be careful how you interpret G to the power J, yeah? Because we are computing now with it. Since we have compositionally conjugated with phi, I should perhaps be more careful and write in C in less than infinity phi. In other words, we now equip C less than infinity not with the usual derivation, but with phi inverse times the usual derivation, which we called this funny delta, right? In other words, G to the G has to be understood as follows. It is G to the power G0, and then delta G to the power G1, not the ordinary derivative of G, but the funny derivative of G to the power G1, delta RJR, delta equals inverse delta. So we work with this derivation now when we evaluate c to the j. Right. But what does this say? This says, this gives you delta k of g bounded. Yeah, here again, I wrote in c less than infinity, but if I wanted to be a little bit more accurate, I should perhaps say, because the derivation I'm using is subset means that I'm working in this differential ring rather than in c less than infinity usual derivation. Okay. And the thing is, so this says that all these delta kg are bounded, but then these are also bounded. Yeah? All these gj are bounded, dominated by 1, which means since the hj's are negligible compared to h, this means that h is the dominating term in this sum, and so this will be h plus something that is tiny compared to h itself. So therefore, f equals simply h plus, yeah, little o of h if you want, or if you want to be really precise, you simply express it this way: pf is asymptotically equivalent. Well, however you pronounce that, equivalent to little h. Yeah, it's h plus something that is strictly dominated by h, and therefore it certainly is a unit, right? It's h times 1 plus little o of 1. So pf indeed a unit. And so this being true for any non-zero differential polynomial, we have a Tardian and we have this I being a true limit. Right. So this is showing a key step, but that is what we are going to use to verify that we have pseudo limits. What's the time? Oh, 9. Okay. Now, another thing that is worth saying the thing is that 2, I hope I didn't, yeah, maybe I better do it on this blackboard because I want to keep this this statement on the blackboard. Yeah, if you look at the proof of 2 implies 1, you see that you can actually replace 2 by something that is a little bit more convenient for us. There are several variants of 2, of condition 2, that are just as good, but sometimes more convenient. Mark. And place 2. Call it 2 star. Which is all n bigger than k. All bigger than k. Active. Well, maybe I should say that is. Let's say there are arbitrarily small. Arbitrarily small. Yeah, here we quantify universally over all active phi, but of course it's enough to consider sufficient small, arbitrarily small phi active phi bigger than 8. And it's bigger than 0 is also not very important. It's just, how shall I say? Because later on we actually work with these. We replace compositional conjugates H hat phi by actual conjugates with compose with certain functions, and we replace it by an actual Hardy field, but for that we need phi to be greater than 0. Small active phi such that delta k f minus bounds. Delta. Right. Okay. Yeah, same proof. I mean, when you go through the proof, you'll see that it's just take some phi that works, take it all sufficiently small active phi, and you just take some of this constant proof. Right. Now, in order to use this test, we really need to transform it. We need to express these powers of funny delta in terms of delta itself. So expressing, this is a little subsection, if you like, expressing powers delta k terms of the ordinary definition. This is basically the kind of thing that's done in also in our book. And let me just check the section 5.5. Remember delta. Let's to simplify notation. Let me just write f delta and f. Then have delta to the k equals sum j 1 k g aj f delta to J. Yeah, I mean, if you like, yeah. Again, in this ring, of this differential ring, where the GKJ are certain homogeneous, and that's important. GY are certain differential polynomials just with rational coefficients which are totally independent of everything. They only depend on K and J, not on Charlie fields we are in. But it was where we assume where we view this as a subring of. Right, so we evaluate this according to the usual derivation, right? That's why I'm writing HY and not HVY. And right. HK is homogeneous. Degree K, that is important actually, and of order less than equal to 5. I think I actually had such expressions on the blackboard. I mean, for K is 1, you just have that delta equals F times delta J, so G11 would just be Y itself. Yes. Say again.
Order
Of order less than or equal to what do I mean? Yes. Order less than equal to K. Yeah, less than equal to order K. Yes. But no R involved at all, of course. But because it's homogeneous, and simplify this, well, simplify. For us, it's useful to rewrite this a bit. Now, say, oh, GKJ F is, you see, you can factor out F to the K. And then you get something that is a Riccati. That is sort of the Riccati polynomial corresponding to this homogeneous. We have a differential polynomial that is homogeneous of a certain degree, and if you then factor out y to that degree, you get yeah. Then anyway, what you get here is then something that's like a Riccati differential polynomial applied to the f dagger. Right, so you can exchange f for f dagger by factoring out f to the k. And here rkj is, let's say, we use a different variable z. It's into z. This is of shall I say, of order less than k. Yeah. Typically, the order goes down. Anyway, but it's not homogeneous anymore. So you lose something. But nevertheless, this is a useful. So therefore, what we get out of this is that therefore, that's something. With a double star. If I now plug in anything from this ring, you get delta, the Kate funny derivative of any element G equals, for each of those you factor out f to the k, but f is phi inverse, so this is phi to the power minus k. Sum k is 1 to k, rkj, and this becomes minus phi dagger. But you see, we have a very good control over for phi active and small. We have reasonable control of size of this times the ordinary J derivative of G. Okay, for G, again, in this ambient differential ring. Right, so the Kate funny derivative of G is now expressed in terms of derivatives, the ordinary derivatives of G, involving phi and phi dagger, but in a way that is not too bad. I guess I have to. I never said that k here is at least 1. Well, for k is 0, there is really nothing going on. Right, I mean, strictly speaking, this is not true for k is 0. Because then this would be the sum of j is 0, 1 up to 0 would be 0. The delta to the 0 is simply the identity. So this I should have said k greater than 2, 1. K0 is really nothing worth saying. Okay. Yeah, so that is one little ingredient that we will later need. So now, okay, and we need to go through another little ingredient, namely, but maybe I'll wait a few minutes, 5 minutes, and I'll start at 10 past 10. Yeah. Anyone has an idea about this question? Remember in Hardy's book, Orders of Infinity, just quote some results of people like Poincaré, who prove things like for every continuous function on, let's say, some half line, you can find an analytic function which difference with that continuous function, small as you want, in some error function epsilon might even go to 0. And I guess one can probably use this to prove something like that if only finitely many n's are involved. But now all we want is for all n. things there. But you see, you can take smaller and smaller end intervals. F minus G bounded by some constant might hold on an initial interval, and then on some much smaller interval, F prime minus G prime might be also bounded. Then on a still much smaller interval, F2 minus G2 bounded. So you do have a lot of freedom to left. So I'm not. I think this is not totally hopeless. This could be, for all I know, could be true, and be interesting to know either way. I hope that someone knows some literature, these things. Was probably a time that, like 100 years ago, that such things were known. But keep this here. Making things smooth. I mean, this goes back to, yeah, let me start again. Yeah, when we were talking about pseudo-convergence of Hausdorff fields, we were able to construct pretty easily some pseudo limits in the form of infinite sums, which pseudo limits are of course continuous terms, but when you work in Hardy fields, eventually at least n times continuously differentiable for every n. And so yes,
I think the microphone. Just double check. Oh, I see. Okay. No, the batteries are low, so I just need to change things out. Sorry. Just need 1 second.
okay.
Something.
Thanks. Okay, so yeah, when you want to smooth things out, it's fairly standard to use certain functions. Like this function that is 0 for arguments less than 0, and then increasing. Yeah, so fix a C infinity function alpha from R to R, which gets alpha, let's say alpha t is 0, well, let's say alpha is 0 on minus infinity 0, alpha strictly increasing, or at least increasing. I guess it doesn't really matter too much here. On from 0 to 1, and identically alpha is 1, or 1. So such functions are well known, but we are going to use a variant of that, where instead of 0 and 1, you have any numbers a and b. But we obtain this from alpha by just some kind of affine change of variables. So, yes, I have to. Yeah, it will be useful to fix bounds on the derivatives of alpha for each n. Cn, it doesn't really matter how big that is, such that first of all, I'm going to assume that they are increasing in size, and the nth derivative of alpha will be less than or equal to Cn everywhere. Yeah. Of course, the n derivative of alpha is 0 here, and alpha and the n derivative is 0 here as well. So it's only relevant what happens between 0 and 1, and by compactness, of course, there is such a bound. And we don't really care what bound that is, but and of course you can take these bounds to be increasing if you want, and that's what we do. Now, for any real numbers a less than b, for any a less than b, set that, so we do alpha a comma b, alpha, again given by alpha, well, and then we take the obvious affine transform of the variable t, and that has the effect. So alpha, that you have this kind of thing with a and b instead of 0 and 1. So alpha ab is 0 on minus infinity comma a, alpha ab increasing on that segment a comma b, and alpha ab is 1 don't be. Right, but what for us it is useful to have also bounds on the derivatives that you can get from that. Alpha, the nth derivative of alpha AB will be less than or equal to Cn divided by b minus a to the power n, if I'm not mistaken. Right. Okay, this will be right. Yeah, I mean it's so. In other words, if b is far away from a, then you see these n derivatives become also rather can become. You can make this as small as possible by taking b sufficiently bigger than a. That will be a useful thing to do. Okay. Okay, so now let H be a Hardy field. Let's n0 again. We have f0 dominate f1, dominate f2, etc. in H, all positive elements, and so then we can form an fi is f0 plus fi. So fi is a sequence. And we would like to have it pseudo converge to oh yeah, right. Now yeah, we are going to take representatives of these terms, take representatives. Well, see. What do I have this? A continuous representatives, at least continuous. Of course, ultimately they will be n times continuously differentiable for fn, fi. Yeah, for minor technical reasons, we will take them as defined on this graph line. Yeah, so I denote the germ fi same. I have the same notation for the representatives, just to. Now, and so that means that so then also fn becomes a function continued. Sorry, yeah. Then of course this finite sum becomes also simply a continuous germ. But now for every n we can take an interval. Yeah, for each n. Take a n so large, take a n greater than equal to 1 so large that fn is of class that fn is Cn on an plus infinity. And we can right. Okay. Now we take also, yeah. Next, take reals C0, C1, yeah, 0 less than C equals 1 less than equal to C0 less than C1 less than C2. Such that first the Cn should go to plus infinity as n goes to infinity, and define set alpha n to be alpha with Cn plus 1. In other words, this we apply this construction now with A equals Cn and B equals Cn plus 1. We will make sure that we will try to adjust the Cn's such a way that nice things happen. But I'm not saying yet. The A's, you can think of the A's as being fixed from now on, but the C's as being adjustable to what we want. Right. So, back to blackboards. Okay. Anyway, alpha n will be 0 for arguments less than or equal to Cn, and 1 for arguments greater than or equal to Cn plus 1, and in between it will be strictly increasing. And of course, it is C infinity function. That's important. Now we are going to adjust the f's, the little f's, by multiplying it by alpha n. So, set little fn star equals alpha n. We just multiply fn with alpha n, and of course that doesn't change the germ at all. So fn star same germ, because alpha n will ultimately be equal to 1. Same germ. But the effect now is that this will be of class, let me see. Oh, I did overlook one little point. F0, I forgot to make sure that these continuous representatives are such that fi plus 1 is less than or equal to a half fi. Yeah. Such that, yeah, in fact, even strictly such that 0 less than fi plus 1 be less than a half or less than or equal to a half it all t bigger than 1. Should you can, just like with Hardy fields, you can always change the initial behavior of these f's. I mean, this will automatically be the case for t big enough, right? Like this one's strictly dominated by fi, but you have to adjust the initial behavior a little bit to make it sure everywhere. But you can do that. since at this point we only require continuity. And of course, right. Okay. The thing is that this will not this will preserve this property, except that instead of 0 less than, we have 0 less than or equal to. That's fine. So Fn, it will still be the case that Fn to 1 star is less than or equal to a half Fn star. In other words, you can still form infinite sums. Thus, but let me see, I want to say one thing about Fn star that I didn't say yet. No, that's fine. Thus we have a continuous function f star. I assume fi star, and yeah, 1 to the convergence here will be uniform on each compact subset. One. And f star minus fn star. Oh, yeah, of course, fn star is also equal to f0 star plus. We simply replace everywhere the fi's by the fi stars and adapt everything accordingly. Right, then f star minus fn star will be satisfy this for all n. We had this for f sum of the fn's, oh, well, actually I have, yeah, it doesn't matter whether I write here fn or fn star, right? I mean, fn and fn star are the same when you go to the germs, and this is anyway. This is also now the lemma that is that yeah, I haven't said what I assume about the CNs, or I'm going to assume now that the CN, let's suppose CN is bigger than the first n a's. The a's are fixed and the CNs are adjustable, so of course I can take the C, suppose Cn bigger than a0 to the n for all n. Then, in fact, this function f star is in C less than infinity. Then, first of all, for all n, fn star is C infinity. Yeah, fn star as a function on one. As a function is Cn everywhere, not just eventually, but f star is of class Cn at least on the interval from Cn to plus infinity. So the germ of f star rising. Yeah, I guess this is really just an exercise, just checking that. Well, it does. I guess it does use some things about infinite sums of Cn functions. Well, no, I think simpler what I suggest. Well, let me see if I should go. Yeah, why don't I go through this? I mean, also, instead of the exercise, I'll give proof which is 4 lines. And now I do this which I'm going to use later on, but since I'm not going to get to that anyway. Okay. Okay, good. The way the CNs are chosen, yeah, alpha n will be 0 for arguments t less than Cn, and that means that fn star is simply 0 on 1 from 1 up to Cn. Yeah, and Fn, but we also know that Fn is Fn of class Cn on An to plus infinity, and Cn was chosen to be bigger than or equal to An. So Fn, so see. So the result is that Fn star is a class Cn. On the whole interval on which is defined. See. Fn star is alpha n of n, right? Okay, so for up to Cn, nothing can go wrong. Beyond A, okay, so 1, here you have An, and here you have Cn, let's say. So here, Fn star is just 0. Here it is Fn. Here it is just Fn, which is known to be, and in between it is Fn multiplied by this alpha n function, which is C infinity. So
Would it be between Cn and Cn plus 1?
let me see. I think what I wrote here is correct, although the argument I gave may well be. I think this is what I mean. I think it's true, but I mean, changing insert argument Cn by Cn plus 1 would be pretty harmless, or it's just a re-indexing issue.
Yes, you pick alpha, that's An to Cn.
This is what this is what you're talking about. Yeah, you're right. I alpha n. So yeah. Okay. Cn is 1. Right. So it's okay here. It's okay. It's okay there. And then well, up to Cn, it is simply still. Anyway, this is. I don't want to spend time on this team verification, and if I can do it now. Okay, for t. Yeah, for t less than or equal to cn plus 1, f star t, what is f star t? It's f0. Of course, this is defined to be the infinite sum, right? But as long as you restrict your arguments to less than or equal to cn plus 1, it will be just this sum. And f0 star t, and f star t. And so f star, right? Yeah, because the later f, of course, it's the infinite sum, but the later ones, fn plus 1 star t, etc., are all 0 as long as they less than equal to cn plus 1. So, and that means that fn f star is of class Cn, is of class Cn. At least on the interval from an to cn plus 1. Yeah, so on this interval. But of course, these intervals are interlocked, how do we say, an plus the next cn, the next interval will cn plus 2, an plus 1. An plus 1 could be either here or there, but see, you get bigger and bigger intervals on therefore f star for the same reason as class Cn on an plus 1, 2, etc. Well, it's actually of class Cn plus 1 on that. Therefore, f star will be class Cn of everything starting with an.
See what the stars. See the star.
As long as you restrict to arguments that are less than equal to Cn plus 1, this is
Coincide.
they coincide because the fn plus 1 star are 0 on below Cn plus 1. So f star is of class Cn on Cn, close to 0. Okay, yeah, that's what we are claiming there. And so, yeah, that's the proof of that lemma. Now, let me see if I, right. Yeah, okay. There are too many things that I would like to keep on the blackboard for later reference, but it's not possible to. Yeah, of course. All these arguments can also be adapted to the Cn situation where you want where the germs, initial germs are C infinity germs, and you want your f star to be a C infinity candidate pseudo limits. That's all easily possible. Okay. Now, I want to get to, yeah, let me now state the theorem that we are, again, yeah, we put ourselves in this situation, right? H is a Hardy field, you have these germs, and you want to show Fi pseudo-converges. Some Hardy field extent. And proof, yeah, proof, let's say proof sketch, because this will be, I don't know, maybe next time I will fill this out a little bit. But, and I'm only going to do this now in the so-called fluid case. And I'll say what that means. But there's the other case, which is causes some trouble to deal with. But the fluid case is this. Fi plus 1 over Fi, if you look at these quotients in our Hardy field, Fi plus 1 divided by Fi is of course infinitesimal, right? These are all infinitesimal germs, but they could be, with a little bit of luck, all less than a fixed infinitesimal. For some fixed epsilon. Now, it's not a real number, but an infinitesimal germ in H and all I. They are all infinitesimal, but of course it doesn't guarantee that they all are below a fixed infinitesimal. By the way, this will be the case if the cofinality, if, well, what is it? If you look at infinitesimals in H, and there is no small, there's no, if the co-initiality of the infinitesimals is uncountable, then this will be the case, right? Will be the case if the co-initiality of H, well, let's say positive but infinitesimal, greater than 0. So this is the set of positive infinitesimals. If this is uncountable, right? Because then each of these is infinitesimals, but because there is no countable co-initial sequence, there must be one that is below all of them. Wait a minute. What am I? I guess I'm doing it the wrong. Or am I doing it the wrong way around? Co-initiality.
This is the same thing as cofinality of H.
To get confused with something funny here. Co-initial, if it's uncountable co-initial, this means that there is an epsilon that is smaller than all these things, right? Instead of the other way around. Now I'm confused. Wait, they're all, right. It's the cofinal, no, it's the cofinality of the, You want a big infinitesimal, right? It's the cofinality that should be bigger than omega, right? Of course, this is the same as the co-initiality of H bigger than R. Right. So if yes, right. And so you would think if we could prove this, if we could prove for maximal Hardy fields, for example, that the co-initiality of this is uncountable, then we can always reduce to this case. But unfortunately, we don't know a direct proof of that. We have to, we know this after the fact, after our main theorem is proved, or after, let's say, this theorem has been proved, we do know as a consequence that these co-initialities are indeed uncountable, but before proving it, we don't know it, and we don't know how, or we don't know how to prove it, and so we cannot use this, the fact that this is true for maximal Hardy fields, unfortunately. And in fact, I noted that Boje Nitsan also asked whether the co-initiality of a maximal Hardy field is, whether these co-initialities are bigger than omega. That was an open question for him. Right, so I have 10 minutes left. I can't do too much, but we can, of course, always. So we assume this. Yeah? We are going to assume that we have a fixed infinitesimal epsilon, such that all these quotients are strictly dominated by it. We can, of course, pass to a closed. Passing to a closed. To an H-closed extension. Yeah, arrange H closed. Yeah, here we'll close omega free Newtonian. Yeah, okay. I said that see that I said that in the ski lemma that was the only place where we used our main theorem, but in fact I now realize that here, of course, we also use for the second. But it's okay, yeah, right. Can also replace H by H, and now we G inf for G bigger than R, and, let's say G and H. Right, so for G. The thing is that then the FI's get replaced by this replace FI then by the corresponding FI. This is again a Hardy field. It's still actually H closed. That's another thing that when you do this kind of composition, H closed is preserved because this corresponds to really compositional conjugation to an active element that preserves H closeness. Just replace Fi then by Fi also G inf, etc. And note that Fi will pseudo-converge to F if and only if Fi composed with G inf, which is all these little maneuvers are straightforward. The point is then that by doing this kind of maneuvering, you can arrange that this epsilon is simply e to the power minus x. Yeah. So in this way, choosing g equal to well minus log epsilon. Rearrange this way. That's all fi plus 1. Of course, the new fi plus 1s are really these, fi's are really these, but I'm not going to. I'm adopting, I'm changing my notation so that this is now fi. Fi plus 1 over fi is e to the minus x. Right, all I. And so far, yeah, now we are going to do this. Let's see. Ah. I think I erased certain blackboards that I should not have erased. The thing is that we now do carry out all that stuff, make everything smooth, and right. Yeah. So as we take A0, A1, take representatives, Fi and reals 1 less than A0 and reals AN greater than 1. And C0 less than C1 less than C2 as before. So these are going to be fixed, and these are adjustable. Fixed. Adjustable. But Cn bigger than all the A0 up to Cn bigger than A0 up to An. As before, and such that giving us Fn star is 0 star plus before the actual sum of n is 0 up to infinity f star now element of C infinity as yeah. Now it becomes a little bit yeah, I think in the next 5 minutes I could only introduce extra notation that and I cannot really act on it, so I think it's better to stop here. But I see, you can see that I carried out some of the obvious maneuvers that one has to do. Of course, we have to verify the right. So with capital F star instead of F and Fm star instead of F, Actually, I don't remember. It doesn't matter whether here you have f star, whether here you take fm or fm star, I'm not sure. Neither do I. Have to look at. You see, let me just say what we are going to prove ultimately. We have to make estimates and we have to choose the CNs in a very careful way, well, not that careful, such that ultimately we will able to show that the k funny derivative of this quotient f star minus fm star divided by little fm evaluated as t will be less than equal to the power k plus 1 power 2k to the power minus t. K between 1 and n. And t greatly equal to some number that depends on still another number, Cm star, which depends on Cm in a certain way. Right. You see, by doing a little bit more maneuvering and making careful choices on the CNs, we will ultimately be able to put this bound.
Divided by the fm star.
No,
fm.
I divided by fm. In fact, you see there is a little thing, fn star is actually 0 on an initial segment, and fm we have chosen it to be strictly positive. So I actually do mean this, but if actually it doesn't really make too much difference because we are going to restrict ourselves. I guess you could simply also take fm star here because ultimately it's the same. Agrees with fm far in the other way, right? But it's more convenient to do it in that form anyway, because f star and because fm star and fm have the same germ, also capital F star, capital FM. This will then tell us that using that test here, that the Fi's will pseudo converge to F star, and F star will be more important Hardian over H and that. But this is ultimately what you see. E to the minus t is dominating, right? You see that this so this will be because of this bounds. This will be this term will be dominated by 1. Right. So, but you see, the estimates are take about a page to do, and it's a little too much to carry that out in the last minute. So. Of course, we are going to use this expression for funny delta to the k. Okay, so